This is the first of 3 videos talking about section 4.9. In this video, I'll talk about antiderivatives. So what is an antiderivative? So a function capital F is an antiderivative of little f if the derivative of capital F is equal to little f. So the idea is that we're starting with little f, and instead of asking what the derivative of little f is, instead what we're looking for is a function whose derivative is little f. So we're kind of giving the answer to the derivative question, and we're trying to figure out what the original function was. So as an example here, if we're given little f of x equals 12x squared minus 10x, we can see that capital F equals 4x cubed minus 5x squared plus 17 is an antiderivative. And the way that we check that is very easy. We know how to take derivatives, so we're going to just take the derivative of capital F. Derivative of 4x cubed is going to be 4 times 3x squared. Derivative of 5x squared is going to be 5 times 2x. And the derivative of 17 is 0. That works out to be 12x squared minus 10x. And since that is little f, that checks. Now, why am I saying an antiderivative here rather than the antiderivative? Well, what you might notice is that that plus 17 didn't really matter. The fact that there was a plus 17 there, when I took the derivative of the 17 was 0. And so it didn't matter that it was 17 instead of any other number. So in fact, any function, capital F of x, which looks like 4x cubed minus 5x squared plus c for any constant c, is also an antiderivative of that function little f. So one thing we're noticing here is that when we look at antiderivatives, we don't just get one answer, we get a whole bunch of answers that all look pretty similar. The only difference between those different answers that we get is that they might have different constants. So let's look at some more examples. So what if I said find all antiderivatives of little f of x equals secant squared of x? So again, the way that we're going to think about this is what we're looking for is the original function so that when we take the derivative, we get secant squared of x. So the question is, what goes there? What goes in that spot? So if we think about our knowledge of derivatives and we think about our derivative rules, hopefully what we realize after a little bit of thinking is that if we put the tangent of x in that bracket, the derivative of tangent of x is secant squared. So the capital F that we're looking for is tangent of x. And then again, we realize that actually tangent of x plus any constant, if we take the derivative of that constant, we'll just get 0. So that is all of the antiderivatives, or sometimes we call this the general antiderivative. What about 7x to the 6th? Again, the way that we're thinking about this is we want to think, okay, what would I have to take the derivative of so that the answer would work out to be 7x to the 6th? And again, thinking about our knowledge of derivatives, doing a little bit of maybe trial and error here, we would see that it's x to the 7th. When we take the derivative of x to the 7th, the 7 comes down, 7 minus 1 is 6, we're using our power rule there, and so our capital F of x here would be x to the 7th, again, plus a constant, because adding that constant doesn't change the derivative. So the notation that we use for all of the antiderivatives is what we call the indefinite integral notation. So this skinny s thing, that's called the integral sign. And then after the integral sign, we take the function. So little f of x here is the derivative, and we're trying to find the antiderivative. And the dx here just means with respect to x. And we've seen in the past how it's important to keep track of what variable you're doing your derivatives with respect to, so it makes sense to have our antiderivatives also be specific and know what variable are we taking the antiderivative with respect to. So with this integral notation in hand, we can take the problems that we've worked on so far and just rewrite them in this integral notation. So the way that we would read this first one is we would say the antiderivative of 12x squared minus 10x with respect to x is 4x cubed minus 5x squared plus c. Similarly, the second bullet point there, we would write the antiderivative of secant squared of x is tangent of x plus c, and the antiderivative of 7x to the 6th is x to the 7th plus c. All right, so what we're looking for now is to try to develop some rules. So we have a whole bunch of derivative rules. What we want to try to do is use those derivative rules to try to figure out some antiderivative rules. So let's think about a power rule. So what we're going for is something that looks like the antiderivative of x to the n is something, right? Because we have a power rule that tells us how to take the derivative of x to the n. So what we're looking for is how to take the antiderivative of something that looks like x to the n. So to help us think about what that should be, let's try an example. Let's look at little f of x equals x to the fifth. So again, when we're doing antiderivatives, the thing we're thinking to ourselves is, okay, if I take the derivative of something, I don't know what it is yet, I want to end up with x to the fifth. So as our first guess, we might try x to the sixth. So does x to the sixth work? Well, not quite. If I take the derivative of x to the sixth, I don't get x to the fifth, I get 6x to the fifth. But it's close. It's not far off from what I want. So the way that I fix it is instead of taking the derivative of just x to the sixth, I'm going to multiply that x to the sixth by 1/6. And now when I take the derivative, what I end up with is the 1/6 is a constant multiple. I take the derivative of x to the sixth using my power rule, I get 6x to the fifth. And then the 1/6 and the 6's divide out there, and I get x to the fifth just like I want. So that checks out. So the antiderivative of x to the fifth is going to be 1/6 times x to the sixth, and again, plus c. So what would our rule for x to the n look like? Well, it looks like we're going to take our original power, we're going to add 1 to that power, and then we're also going to divide by that new power. So our power rule is going to look like x to the n plus 1, and then we're going to multiply that by 1/n plus 1. And then, of course, we'll have a plus c. Now, there's one slight problem here. If my power happens to be -1, so this doesn't work, if n happens to be the number -1, because then I would be dividing by 0, and that's not going to give me a good situation. So we're going to talk about that specific case a little bit later. But what we have for our power rule is that we have this expression here, and it doesn't work when the power happens to be the number -1, but it works for all other powers. So here's my power rule. So the antiderivative of x to the n is 1/x to the n, 1/n plus 1 times x to the n plus 1. And again, because we're taking an antiderivative, we want to have that plus c there. What about some other rules? Again, these are going to follow from our derivative rules. We've got a constant multiple rule that works a lot like our constant multiple rule for derivatives, which is that if you have a constant times a function and you want to take the antiderivative, you can just have that constant times the antiderivative. And sum rule, again, similar to the rule for derivatives, the antiderivative of a sum of two functions is the sum of the antiderivatives. All right, let's use these rules now to do some examples. So we've got this function, which is a bunch of things added and subtracted together. So just like we would have done for derivatives, we're going to break this up into a bunch of separate problems. So the antiderivative of 3x to the fifth plus the antiderivative of 2 minus the antiderivative of 5 times the square root of x. And then because we've got a 3 times 0x to the fifth, just like for derivatives, the 3 is a constant multiple. That's going to stick around. And we take the derivative of x to the fifth. And just like before, we get 1/6 x to the sixth. What about the antiderivative of 2? Well, there's a couple different ways to think about this. One way to think about it is the way that we were thinking about antiderivatives before. Because if we think to ourselves, okay, what would I have to take the derivative of so that the derivative would work out to be just 2? Maybe after thinking about that for a little bit, you might come up with 2x. If you take the derivative of 2x, you just get 2. Another way to think about this one is to think about it using the power rule. Because I can write in an x to the 0 there. X to the 0 is just 1. And now I can use my power rule. Because remember, our power rule works as long as the exponent isn't -1. Here my exponent is 0. So my power rule would say add 1 to that power, add 1 to 0, and then multiply by 1 over that new power. What about 5 times the square root of x here? Well, we can rewrite this as 5 times x to the 1/2, and again use our power rule. The 5 is a constant multiple. I add 1 to my power, so add 1 to 1/2, you get 3/2, and then divide by the new power, so 1 divided by 3/2, and then finally I have a plus c. Now, technically I get a little plus c at the end of each of these little antiderivatives, but then I could combine them all together into one big constant at the end, right? So if I had a bunch of constants all added together in my function, I could combine my like terms and get one big constant at the end. So that's typically what we do. And we could clean this up if we wanted to. 3 times 1/6, that's 1/2. 2 times x to the first, that's 2x. Dividing by 3/2 is the same as multiplying by 2/3. So this fraction right here, that's the same as 2/3. 5 times 2/3, that's going to be 10/3. X to the 3/2, and then plus c. So that would be my final antiderivative. All right, what about the antiderivative of sine of x? Again, we're thinking about our derivative rules and seeing how we can apply those to our antiderivative rules. So we're thinking to ourselves, okay, what would I have to take the derivative of to get the sine of x? Well, again, thinking about our derivative rules, you might think, oh, maybe cosine of x. So what if I put cosine of x there? Does that work? Is the derivative of cosine x equal to sine x? And we realize, no, it's not, because the derivative of cosine x is minus sine of x. So that doesn't work. So how can we fix it? Right, we're close, we're off by a minus sign. So instead what we'll realize is that if I take the derivative of negative cosine of x, that negative represents a factor of -1, which is a constant multiple. And then the derivative of cosine x is minus sine of x. And so that would give me the sine of x that I want. And so again, doing a little bit of trial and error, a little bit of detective work, we figure out that our antiderivative is minus cosine of x plus c. All right, what about the sine of 2x? Okay, well, again, might try this out. We learn our lesson from the previous one, right? Again, we're looking for something that works out to be the sine of 2x. So we realize, well, cosine of 2x, that's probably not going to work because we're going to get a minus sign. So I'm going to put in another minus sign to see if that gives me what I want. Let's try it out. Well, we get -1, and the derivative of cosine 2x is going to be minus the sine of 2x, but then multiplied by 2, that's coming out of the chain rule. So we fixed the minus sign problem, but now we're getting an extra factor of 2 that we don't want. So what do we do about that? Well, again, if we've got an extra factor that we don't want, we can cancel out that factor by putting in an extra factor of our own. So if I want to get rid of a 2, I'm going to put in a 1/2. I need a minus sign to get rid of the minus that I'm going to get when I take the derivative of cosine. So I'm going to need minus 1/2 cosine of 2x, and again, plus a constant. So again, a little bit of trial and error. Let's check this one. Let's just make sure. So the derivative of -1/2 cosine 2x plus c, the -1/2 is a constant multiple. I take the derivative of cosine of 2x, I get negative sine of 2x, multiplied by 2 by the chain rule, and the derivative of the constant is 0. Minus times a minus is a plus. This 1/2 and this 2 divide out, and so I just get the sine of 2x like I wanted. That was my original function, so my antiderivative checks out. All right, let's do this one. So we've got dx over x. Now you'll see this sometimes where we'll treat the dx kind of like it's a number, and that's really just for kind of notational convenience, but it does make it a little bit confusing to look at. So instead what I want to do is rewrite this as 1 over x times dx. So 1 over x, that's x to the -1, and that means that we can't use the power rule. The power rule for antiderivatives doesn't work when the power is -1. So what do we do? Again, we're just going to think about our derivative rules and see if we can figure out what function could we take the derivative of that would give us 1 over x. And again, thinking about our derivative rules, looking at our big list of rules if necessary, we'll see that it's actually the natural log of the absolute value of x. So that's our antiderivative, natural log, absolute value of x, plus c. One more, antiderivative of e to the 4x. Again, thinking about our rules, thinking about what we can do. What's the derivative of something that would give us e to the 4x? Well, if it was e to the x, I think we could figure out that that's going to be e to the x. So maybe even though it's e to the 4x, maybe it'll be e to the 4x. But again, using our derivative rules, that's not going to work because when we use this and use the chain rule, we're going to get an extra factor of 4 when we actually try to take that derivative. So how do we get rid of that factor of 4? Hopefully you're catching on by now. We're going to put in a factor of 1/4. So 1/4 times e to the 4x plus c. Again, let's check this one. If we take the derivative of 1/4 e to the 4x plus c, The 1/4 is a constant multiple. We're using the chain rule to take the derivative of e to the 4x. We get e to the 4x times 4. And then the derivative of c is 0. When we simplify that, this 1/4 and this 4 divide out. And we again just get the function that we started with, e to the 4x. So hopefully what you're seeing here is that the way we're going to think about these antiderivatives is a little bit of guess and check, a little bit of trial and error, but it's educated guessing. We're using our knowledge of derivative rules to figure out what function would give us the right antiderivative.